So we have Johan and Bill. They are both Googlers, and Johan oversees the speech technology group at our New York office here, and Bill works on voice interface design for both product and research, including design work on voice search for google.com. So I'll leave it to you guys.
Good afternoon. So I don't know if everybody's seen this video on YouTube a long time ago from Steve Ballmer at a developer conference. I mean, he was going developer, 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 and going nuts. So I don't know if you've seen it. Raise your hand. So today I'm going to go quality, 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 and hopefully I don't go nuts. But this is really what makes the product work. And this is really what our group is about. So first, a quick introduction to what we do with speech at Google and why we're doing it and where it's being used. Our aim is to kind of make speech ubiquitous. We want it to everywhere where you need to do input modality to have speech. It's on google.com, it's on the phone, it's on an iPhone, it's on Android. We use it in YouTube for transcriptions. We use it for voicemail in Grand Central. We just want to make it as ubiquitous as the keyboard, and it has to work in order to be ubiquitous. So before we get into more of the technology, Bill will switch over to Bill to just give a quick intro and demonstrations of what this is about, so you can have more context.
Yeah, we found in earlier talks that sometimes people have never used this very much, or sometimes they have, but for the people who don't know what we're talking about, we might as well show you so we can get started. So I'll just do quickly a couple of demos. One will be search, one will be like a voice action, and then there's another thing called voice typing that you'll see later in the talk. But what I'm talking about is this. So I can do a search, United Airlines flight 901.
United Airlines 901 from Frankfurt to San Francisco is delayed and arrives in 1 hour 38 minutes.
Okay, so obviously search, you could say pesto recipes, you can do different things.
Did anybody hear the voice in that?
Yeah, I'll show it to you again later. You can on Android, of course, you can do more than search. You can actually do action. So if you wanted to call something or find a map of something, etc. So if I wanted to call my favorite pizza place, I could say, call Pizza My Heart. And since they're both in my contacts, in fact, it didn't have to be in my contacts. It found both Peter Lindley, which was because it wasn't, I guess, that recognized well, but this is the one I want, and it would just go ahead and call. Of course, I don't have my thing turned on. Another thing that would happen if it is a brand new thing that I've never called before is you'd see a countdown, and I'll show you that again. The last thing is when you actually dictate by typing or dictate by speaking, and that's what we're going to show later, and that's called voice typing for now.
In order to give you context of the technology and what we do to make it better, I thought to try to explain in one slide how recognition works. So hopefully after this you can go code your own recognizer. The audio comes in and we do feature extraction. So this is spectral analysis, where every 10 milliseconds we extract the slice, do the fast Fourier transform, and we get to what we the spectral. From that we extract features. The features are modeled using this thing we call an acoustic model, using a Gaussian mixture model. So the acoustic model models the acoustic space in a hyperdimensional space. And then using the language model, this is like the grammar of English, and pronunciation model, these are the basic sounds of English. We create this graph. So this graph is moth, mop, pop, top, all the different ways of saying words. And so using the acoustics, the acoustic model, the language model, and the lexicon, we create this giant search graph, and we do a fairly large Viterbi search of the space in real time. So as you speak, we go through this giant graph, millions of nodes and interconnections to basically determine what you said. Yep. So a lot of our work goes into these models: acoustic model, language model, and pronunciation model. So one way to improve acoustic models, speech recognition, is to improve the way you model the basic sounds of the language. And one way is to get lots and lots of data. We train on hundreds and thousands of hours of audio from our live system, and that you get all the accent variations. So the traditional system, and this is what most or all speech recognizers to date that are deployed by by other companies uses called the either Markov model that uses a mixture of Gaussian. So Gaussian is this bell-shaped curve where you can model this acoustic space in a hyperdimensional. And the more parameters you throw at it, the more Gaussians you can start modeling the finer details, the co-articulations, the accents. And that works really well. This is how we built our systems for the last 6 or 7 years I've been at Google. Another way to do it, and this is kind of interesting, I worked on this personally about 15 years ago, is to use neural networks. So neural networks is inspired by computations in the brain. We have these neurons that then activate and send a signal to a neuron. And so I just say inspired by what is actually, it's a very large nonlinear function which is consisting of an input layer, where are your features, the hidden layer, which computes some representation or higher level representation of the features. You can think of in image segmentation lines, in speech maybe phonemes, and then the output layer, which are the classes which then are used to do the search. And so I'd worked on this 15 years ago. It kind of died out a little bit, wasn't working so well. In the last 2 years or so, it had a resurrection. And at Google, we've got a fairly big breakthrough using it, what we call deep neural networks. And it's deep because we stack multiple layers. And also Moore's law has helped this, because when we did it 15 years ago, it just took a horrible time to train. Like you would days and days, and this was on little data. Now we have hundreds, thousands of hours of data, and a lot of computers, GPUs help. And we are able to train what these deep neural networks. And the effect, we'll show in this graph of our research in the last couple of months, is, so I'm not showing the absolute word errors because it's very dependent on the task, but every bar here is about 15 to 20% better than the previous bar. And these gains are sort of kind of unheard of in the speech community. When you get a 5% gain after many months of work, like you jump up and down. And here we're talking about 15, 20% gains. And you see this when you start using the system and you speak to it, and it just gets you words. And this is what is required. Yes?
Why are you getting those gains?
The neural network.
So what's different now than 15 years ago? Say it again.
So one is the ability to train very large networks on large amount of data. The other, there were algorithmic advances made in the last 2 years to make neural networks trainable and to solve some of the optimization problems that we've had before. So it's a combination of computers helping us and smarts from humans.
So the breakthrough is more, there's a little bit of breakthrough in terms of intellect, but more breakthrough in terms of just sheer computation.
That's one big part of it, yes. Okay. So that's just in order to recognize the words accurately. But another aspect of deploying speech recognition systems is what I call latency. So how long would you wait for, when you speak something, for the words to come back? Would you wait 5 seconds compared to typing? Would you wait 10 seconds? Probably not. It's really, really important that you get the answer back really quickly. And so we concentrate at Google in search and in speech a lot on just getting the latency. We measure things like what is the 50th percentile latency. That's the average. But average doesn't tell you a lot. Maybe the 90th percentile is 4 seconds. That means somebody at the edge of our curve is getting 4-second experience. That's really bad. So we optimize the 90th percentile latency to be less than a second. Okay. So then another way to improve latency is also give the user early feedback. So we can switch over to Bill to show us kind of the effect of this.
So what I'll do is I'll show a voice typing demo where we're using if you can see up here, there's a microphone on the keyboard, and I voice type, right? I say things, and it's as though I'm typing. And you'll see how it works in real time. I love to give talks where whoops, I don't want to go up there. Hold on, stop, wait. I want to do it actually in the message because I don't have anybody named that. Sorry about that. I love to give talks where I can demonstrate real-time recognition, almost. So you see there, the words are coming back as I speak, whereas just, I don't know, it wasn't even a year ago that we didn't have that feature. We just had, you talk, we'll wait, and then blunk, and this becomes a new thing that we can do. So continue on, please.
Before this, I had this kind of joke I used to call about speech recognition sometimes. Is you call it say and pray. Like you speak, you wait. Is it going to be right? Oh, it's right. Here you get real-time feedback as you speak what was recognized, and so the system feel much more responsive. Okay. So another aspect of products like these is connectivity, and the reason why is all recognizers today that you speak to, Siri on iPhone, Google Voice Search, search on Chrome, is cloud-based recognition. That means you start streaming the audio as you speak in real time up to the cloud. You recognize those in real time. The words are streamed back from the cloud over the wireless network to your device, and the words are displayed. So just what we saw now, build it in real time, that was going through our data centers, computing, coming back all in real time, so that you don't feel. But a problem with that is, what if you don't have a connection, or you're a very crappy 2G connection on the ski slopes or something? It just doesn't work. And this, for voice search, when you're trying to do United Airlines Flight 901, it really makes sense that you're connected because you're trying to search Google. If you're trying to type a message or maybe a document, do you have to be connected? This is part of the keyboard. Imagine if the keyboard had to be connected to the cloud. Every time you press a letter and it says, sorry, no connection. Keyboards can't work like that. And so we felt fairly passionate about that voice search on the keyboard, voice IME on the keyboard should also not be constrained by the cloud. So what we did is we took this very large recognizer that lives in our data centers, and we shrunk it down to fit on a phone. And that did quite a feat of engineering and algorithmic design. Algorithms that use floating point arithmetic now to become fixed point. Large data structures for encoding language models have to be redone in order to fit in the memory constraints. CPUs on phones are getting a lot better, but they're nowhere near what you get in the data centers. So Bill will quickly show that, and we're going to do the same type of demonstration of voice typing, but now in airplane mode. So there's absolutely no connection to the network.
Hold on, my toggle has turned off.
Tell your phone to fix it.
No, my projector is turned off. Did I kick off the... Oh, here we go.
Okay.
I think. I think the microphone hit the button. Or not? No, it's not on. See, there's no power. I've lost power. Well, why don't you continue, and then we will show that particular demo, which is really cool, when I go to my part.
Yeah. Okay. Then, so far I talked to him about just recognizing your speech, turning it into text, doing it really fast, always connected to the cloud. In the demonstrations we saw earlier, and this is part of the private Google Voice Search on Google Now that was shown at Google I/O, you heard the system speak back to you, say United Airlines Flight 901, and then it speaks back information to you in a nice and natural voice. And so that's another important aspect of a high quality product, is when you speak back, it doesn't sound robotic. It sounds like a natural human and giving you the information that you asked for. And in order to make that happen, we have a fairly big set of technologies that have come together for doing speech synthesis. So to build a good synthesizer, you kind of first have to find a voice talent, somebody who speaks in a nice way, in a natural, friendly way. So there's a big process of casting voice talents and figuring out, will this match the product from a personality perspective? Some people's voices are not that good for building synthesizers, so will that help? How you read text, 24-7, what does that mean? Is it July 24th, the 24th of July? Maybe it's a fraction. It all depends on the context. So taking text and speaking it out naturally is quite a challenging problem. When you're speaking to a person, and my last name is Schalkwyk, and whenever I say to somebody, then they say Schalkwyk, and say no, it's Schalkwyk. So what is your pronunciation? When a system that reads back to you pronounces something incorrectly, like El Camino Real, if that pronounced El Camino Real Road, it's spelled real, R-E-A-L, but it's real. So pronunciations is extremely important to getting a good voice output. Then we take all of this data, the text, the audio data from the talent, we break the audio into tiny little chunks we call diphones, and based on what you ask to say, we string them together and we produce natural sounding speech. What you might have heard. Okay. So
let's go back to your online demo.
Okay.
So I'll switch back. We just simply had the power unplugged here. But you'll notice now that I'm going to put the phone in airplane mode, which means we don't have a connection. And we'll go back and do the text message again. And you'll see that with probably very little difference, it will still be able to recognize and print what I say. I don't have any connection to the internet, yet I can recognize speech. So that's pretty cool. That's not been done before this well, I don't think, on a phone.
That's correct. Yeah. And this coming back, and also kudos to our team. The amount of work to get that to fit in the resource constraints of a phone was just incredible. So lastly, we're going over to speech interface, where I'll hand over to Bill. We can make the recognizer really accurate, a lot of engineering and algorithmic research. We can make the voice sound really great. We can make it fast and connected. At the end of the day, it comes down how you put these together. A good user interface will make or break the product. If you don't have a good interface, it won't be usable. You will feel clunky, no matter how good the technology is. So it's really important that you also solve the problem at the user interface level. And this is another aspect of quality.
Okay, so what I'm going to do for the rest of the talk is mostly just demos. You know, what Johan says is exactly right. However, I would say that the most important thing for user interface is a good recognizer that's accurate. So it still trumps everything else. There's no question about it. So these are kinds of the things I'm going to talk about, but you don't really need to follow this. You'll just need to follow me in my demos and we'll be fine. So the first thing I want to say is what I just kind of said there was, you know, speech recognition still these days is, you know, an inherently limited interface just because of the recognition. We know that it's not 100% accurate. And so we have tricks of the trade that we've learned for the last many, many years, even when we had phone-only applications and things like that. But of course, now with the advent of the beautiful graphical display plus speech, things have changed. And one other thing to mention is that just like any interface design, this is still in flux because it's kind of still a very new, you know, it's a relatively new discipline where you're trying things. I mean, up until recently, we didn't have, you know, what we call streaming recognition, where the words are printing back as you say. How are you supposed to display those? Should you display it really quick and have them flip if it figures out it has a better calculation, or should you wait? What's the trade-off? These are things that are all in flux. So let me start off with just saying that obviously accuracy is still limited. However, I have to start with an anecdote. The other day I was doing a user study, and for the first time, I've never seen this before, we were doing obviously a speech-based study, but the participants didn't know this coming in. And the first thing I had them do was just remember certain searches, and they were doing them typing, most of them. Now, one of the 10 people was a woman who immediately picked up the phone and did her searches just by speaking. She was the only one, and I said, well, that's interesting. I said, you know, we didn't talk about doing searches by voice. Why did you do that? And she says, well, I have a special third-party keyboard that I like to use, and this is a phone that didn't have hers loaded. And she said, so if I have to use a regular old keyboard, I might as well use speech. Which to me was like, that was kind of a breakthrough, because you might as well use speech. You mean speech is just as good as a keyboard in that case for her. She had things that she had done on her setup that she was not willing to part with. And giving her a regular old keyboard, you know, speech could do just the same as that. So that was pretty encouraging. So let's move over to the, I am on the demo, okay. So let's look at two different interfaces. One is for search and one is for voice typing. And let's look at the trade-offs. Now with search, what's really painstaking is to watch users every time. I'm going to do it in front of you. And you know, a lot of people are like this. They're like, okay, blah, 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 right? So they have to really think about formulating what they're going to say in their head before they say it. And why do they do that with search? Well, it's because, look, on search, we have to kind of endpoint for them because we want it to be fast, as Johan had said. So I don't want, for example, to tap the thing, say my search, and then have to say, okay, go search. I want it to be, you know, as quick as this. Pictures of zebras. So it heard pictures of zebras, it went off and got me my pictures of zebras. Okay? That's not how it works, though, when you're doing a voice typing session, right? So if I go back and I want to do more typing, I actually have to probably stop it myself. It will eventually stop, but I'm kind of more in control here. And the point here is that it's not going off and doing anything. It's not going to leave me do some search, come back and say, is this what you wanted? So there's a trade-off. We could mitigate this, oh no, it's going to cut me off feeling that you get here by allowing users to actually stop it or saying search, go off, and I'll decide when you go search. The problem with that is speed, right? So we've made a trade-off. With search, you do automatic endpointing, go off, even though sometimes people may pause. So if sometimes you see this, pictures of zebras, right? And it only gets pictures of, which is problematic. Do you understand the point there? Question?
Maybe it's a stupid question, but between humans, the tone, do you understand what I mean? The sound of the sentence indicates the end of the search or the end of the text and so on. And is it a challenge, a technical challenge to detect it? And isn't it answering the question you're mentioning?
So all I'm talking about is, to some extent, you have to endpoint and say, we think you're done, we're going to do your search. Whereas in voice typing, you tell us when you're done because there's no advantage to going off and doing them by yourself. But you're saying that the tone itself does, as you heard, it says, we heard, we're going off, too late.
No, the
You
human
stop the sentence and deposit it. So
the human
You're saying better endpointer technology will hopefully solve this problem. Absolutely. Yeah, this is something. Right.
It's pretty hard to extract.
Right. No, but that's a really good point. This is where, in a few years, this is where we want to be.
Do you think that detecting your human tone is still a challenge? Okay.
Yeah. Yeah. There's a lot of challenges that I always wish that Johan would just give me it all. And he's like, come on, Bill. It's 2012. Okay. We don't have that much time, so let me just pick a couple of things to show you. So yeah, just to reiterate this one point, there is this sense of a ticking clock, right? A ticking, I wouldn't say time bomb, but this idea that if you don't speak your phrase in the right kind of quickness, it's going to go off and cut you off. But that's something that you weigh, right? Because most of the time, especially as you're used to this, you say pictures of zebras. You don't say pictures of. But for longer searches, it can be an issue. Let's just do one more and then we'll open for questions since we really do literally have just about 5 minutes left. One thing and I'll show you a different version of Android at this point. One thing that we've done in the past is with these voice actions, right? So the idea was, well, we know that we can do new things on the phone now. We can't just search and type, voice type, but we can also say, listen to Lady Gaga, and you can say send text to Tevis, and you can say, call favorite restaurant, you can say directions to, and you can say navigate to. All of these things are now available, but how do people know that they're available, A, and B, how do they know what they're supposed to say? So on Ice Cream Sandwich, which is what you see here, we have this, nice tutorial type thing that, you have to go off and find, and it'll tell you, oh, if you say it this way, we'll do this for you. But that doesn't work very well, right? How do you tell someone this is how you should say it to get the best results? What's the solution to this? Well, you might have heard Jakob's talk earlier this morning, which is you make it so that whatever you say, we get, right? So in this case, it's not the user interface design, the graphical design or what have you, that's going to solve the problem. What's going to solve the problem is you say, look, you say something reasonable, we'll give you some reasonable results. And if we're not quite right, hopefully one of the alternatives is there. So let me see if I can say, listen to Lady Gaga.
Playing request.
So Lady Gaga, I'll move it along, and she'll probably come up and start playing. Oh, look at that! Isn't that great? So the idea, though, is that I should also be able to say, listen to a song by Lady Gaga. I want to hear music by Lady Gaga. I want to do all of these things, and this is what Jakob's work, especially for voice actions, is doing for us. I think that's an incredibly important point because so much is done to try to solve the user interface when it may be. It may be something that you just can't solve in some kind of fancy user interface way, and you need to solve it by making the technology better. So this is where these two things meet. Accuracy gets better, my job gets easier. NLU gets better, my job gets easier. But in some case, you're going to have to have the right feedback. I think a few minutes left. We should just open it for questions and go from there.
Going back to your pictures of zebras example, people don't usually pause like that. They say pictures of zebras. You can exploit that, or you can ignore it, or you can just have to search for zebras. What do you do?
What do we do in that case? Well, we endpoint and we go off and say zebras.
So you actually do those as words. You don't realize they're just someone
Yeah,
talking.
so fault pauses we can model and ignore them.
Okay.
But if you really just pause quietly, then we kind of think, oh, you're done.
Get into inflections.
Yeah. So if it's a fault pause, then we do model it and continue.
It wasn't a great example. You're right. It's the longer queries where people do pause in very reasonable places, and you're not sure what to do with that.
So when you were addressing it, you spoke in a very different style, which was obvious. So to a human, it's obvious you're addressing a machine, and I'm wondering if you can actually exploit that to automatically start doing speech recognition based on the cadence of the person's speech.
Well, let me just say that I actually exaggerated it a little bit more than maybe I should have, simply because I've done live demos for many, many years, and I've learned it's better to have a good demo than to have anything go wrong. So it does recognize much better than if I could speak much more normally. In fact, maybe it would recognize it better sometimes. But the second half, I think Johan should answer that.
Yeah, I'll kind of emphasize, if you hyper-articulate because you think you're helping the recognizer, that actually makes it worse for us. If you speak naturally, because our data is typically more better natural distribution, then the recognizer works better. So it's kind of more like, just say, show me pictures of zebras, and then we'll do the work.
Do you learn any personalized models, or you use the same generic model for everyone?
So currently, this is what we call a speaker-independent model. It recognizes kind of all the accents that's in our database, and so we get robustness by training on a lot of data from a lot across the country. It works well for my accent from South Africa because that's in our database.
I wonder why.
Yeah, it works well for weather in Scarsdale, New York, because I use it all the time for my testing.
When you ask it, show me pictures, and then paused, wouldn't the natural thing be to do some exercise and grounding for it to say, show me pictures, and then it says,
What pictures you would like to see?
or show me pictures, you say no, of zebras, and then it says yes, okay. In other words, there's a repair dialogue.
Right.
Yeah.
There, that's what humans would do.
No, I mean, I think this is where the trade-off comes, and obviously there's many, many factors that weigh into pushing a product. I think that is something that people are interested in doing and have been interested in doing. You just have to weigh that against, how much does it really improve the product based on the current usage?
Yeah.
So I think that's a good.
Yeah. And one of the important factors there, if you do it well, it's like an amazing experience and you can show it. But you do it a few times wrong, it becomes an annoying experience. And so the cost of a negative there is really bad.
Yeah.
Are you using only voice technology for speech recognition technology for the search application, or you are using also data about previous searches and all the statistics you have about what people usually search and what people don't?
For recognition purposes, mostly it's independent of session. We've done some work where we try to personalize on your voice, and so that we get better for your voice. The gains of that has been smaller compared to, for example, the neural networks.
But I mean, for example, noticing that if you ask for pizza, you are probably wanting a pizzeria and not images of pizza or things like that.
Yeah. So that's more of a search question, I'd say. So we do contextual search, yes.
So in the next 2 years, 1 year, 2 years, where is the breakthroughs going to come, do you think? Or do you expect them? In the computational end of it, throwing more computation, or building better models?
These breakthroughs are a little bit unpredictable in the field a little bit. Like, as I mentioned before, a lot of this work is incremental. You get 2 and 3%, but every now and then there's this big chunk comes out. One area, just looking on the neural networks, we haven't mined everything out of it what it is there. We're just at the beginning. If we can use 10 times more computes, we probably can gain a lot of it. If we can send 1,000 times more data through it, and it becomes algorithmic problems we have to solve. It becomes computational problems. It's just we at the beginning of a new area of research in that domain. And also, if we run out of time, welcome to grab me afterwards and talk to me.
This is a quick question. It just has to do with, do you find any difference in the recognition capability between male and female voices? Because in the early systems, it always had a difficult time understanding me. And they kept explaining, well, it's the tone and pitch of your voice.
Mm-hmm. Yes, and so kind of one, I think, good thing for you is this curve, which I showed, we improving 15-20% is true for females as well. But the answer is yes, we find a difference. Females are, quote unquote, more difficult for us. But part of that is there's less data in our database from female speakers. So we reflect kind of what's in our data, and our data, for some reason or another, doesn't have a lot of female speakers in it. Children's voices also, with the high pitch, are extremely difficult.
Do you think you'll be able to do kids, though?
I would love to. There's a lot of very nice applications you can do with kids and learning and using speech input and output with kids.
Yeah, we really do. I think we really do have to go because of the panel. But thank you, and we'll be around so you can talk to us.